In this video, we're going to take a look at section 6.3, which is on simplifying radicals. We have the product rule that's being introduced here in 6.3, which I kind of used a little early in 6.2 to show you a couple of shortcuts there, but now we're officially introducing it. And so from this point on, we'll just use it as much as we can whenever it's appropriate. So if you have the nth root of a times b, you're multiplying two things inside the radical together, you can apply that radical to each factor individually. So I can apply the nth root separately to the a and separately to the b, and then multiply those results together. It also works in reverse, so that if you have two radicals of the same root being multiplied together, they could be multiplied into a single radical. And you'll just take the a and the b inside of the individual radicals and multiply them together inside of a single radical. All right, so both directions are useful, and you'll have problems where you won't use both in the same problem typically, but you'll have different kinds of problems where you'll use either direction. All right. Okay, so let's take a look at some of these examples. So square root of 45, we want to simplify that. Now, if you think back to the list I gave you back in 6.1 of numbers that you can take the square root of, and I said you should memorize these, 45 is not on the list. Right? So what numbers can we take the square root of? We can take the square root of 4, we can take the square root of 9, 16, 25, 36, 49. We can keep going, but you'll notice 45 is skipped over. Right? So we cannot take the square root of 45 as a whole. But what we can try to do is split up the number 45 in such a way that at least part of it will simplify. We can't simplify the whole thing, but we can at least simplify part of 45 and get some amount of this number outside the radical. So that's going to be our goal here. So we have to think, how do we want to split the 45 up so that when I apply the square root to those factors, something will actually simplify? You don't want to think of the different ways you could split up 45. You want to think, can I split up 45 with one of these numbers in this list? For example, not that you would think of this first, but you could split up 45 as 3 times 15. But that doesn't do you any good. You can't take the square root of 3. That doesn't simplify. You can't take the square root of 15. That doesn't simplify. Neither one of those numbers are on this list. Right? So you don't want to just think of random ways of splitting up the number. You want to think, can I split up 45 with a 4? Because if I can get a 4 there, that will simplify. The answer is no. There's no way to write that with a 4. Can I split it up with a 9? Yes. I can split up 45 as 9 times 5. By getting a 9 here, I know that part will simplify. So we're going to split up 45 as 9 times 5. And then we can use this rule that we were just looking at and split up the square root and apply it to each number individually. So that's what we're going to do here. We'll apply the square root to the 9 separately and to the 5 separately. And then we can simplify. The square root of 9 simplifies to 3. The square root of 5 does not simplify, so we just copy it down and multiply it back to the 3. And that's as much as we can do with that number. That's the most that we're going to be able to get out of the square root. So square root of 45 can be simplified to 3 square root of 5. All right. I've had students in the past where they know, looking at these numbers, they're like, okay, I got a 9, I got a 5. From the 9, I'm going to get a 3. And then they feel like they have to choose, where do I put the 3, where do I put the 5? And sometimes on the test, I'll get students that give me this answer. Right? So I know that they're, setting it up the right way and they're simplifying it the right way, but then for whatever reason, they think there's a choice to be made here of where to put which number. And what I like to point out is there really is no point at which you feel like you should have to make a choice. You just simplify it. If you just follow it in this order, you split the number up, you apply the square root to each number separately, and then simplify the radical that can be simplified. And the radical that can't be simplified, you just copy it down. There's no choice to be made. I don't have to decide the 3 goes outside the radical, the 5 goes inside the radical. The simplifying of the expression makes that choice for me, right? Square root of 9 becomes 3. I simplify it to the number 3. Square root of 5 does not simplify. I just copy it down. And the numbers go where they're supposed to go. That's what I like to tell my students. So you shouldn't have to, there shouldn't be a dilemma here of where do I put this number, where do I put that number. You split up the square root, you simplify where you can, copy down the stuff that you can't simplify. Everything should just go where it's supposed to go. All right. Now, I know this problem looks kind of intimidating. It's a cube root, for one thing. That makes students a little more nervous. And it's a big number. I agree. This one's kind of a tough one on the surface. But if you try, and especially going to be tough if you're doing like how I mentioned over here. Well, how can I write 1,250? And trying to think of all the ways you could split that up. That's a waste of time. You don't care about the different ways you could split up 1,250. What you care about is getting a number here that you can take the cube root of. So make a list, or I mean, I'm going to write it down for you, but in your mind, remember what numbers that I had you memorize from that list that you can take the cube root of. You can take the cube root of 8. The cube root of 8 is 2. So these are the numbers that I can take the cube root of. And these are the only numbers I'm interested in getting here. So I could try 8 out. I could say, let's put an 8 here and see if I can get another number here that multiplies to give me 1,250. You won't. So 8 doesn't work. I don't know what the number is going to be here, but you can find out by dividing. So you take 1,250 divided by 8. It doesn't come out nice. You get a decimal. So 8 is not the number that we're looking for here. What's another number we could take the cube root of? The next one on the list is 27. So maybe we could try to get a 27 here. Again, you'll divide 1,250 divided by 27. It doesn't divide nicely. So there is no other number that multiplies to 27 that gives me 1,250. I shouldn't say there's no other number. It's not a nice number. It's a decimal. It doesn't divide evenly, so there's not a nice factor here that's going to work out for us. So 27 doesn't work. Sorry, I got a lot more to undo there. Okay. The next number that you're supposed to remember from this list is 64. And again, you could try 64 to see if 64 works. 64 times what gives me 1,250. So again, you divide in your calculator and you find it doesn't divide nicely, so it's not a nice whole number that would go here. So that's not the number we're looking for. And you might start to despair at this point, but there's one more number on the list that I said you should know, and that's 125. And you might notice right away that actually works out great. So we'll put 125 here. When you divide that, you'll get 10. It divides nicely. The other factor here is going to be a 10. So 125 times 10 gives me 1,250. And so this is a good number to see here because it's a number I know will simplify. I can take the cube root of 125. It simplifies nicely. So we apply the cube root to each factor separately, right? We're going to split that cube root up, apply it to each number separately. The cube root of 125 simplifies to 5. The cube root of 10 doesn't simplify, so I just copy it down. And then this is my answer. All right. So focus on the numbers that you want to see inside of that radical. When it's a cube root, these are the numbers you see here are the numbers, they're the only numbers you care about with a cube root. So you don't care about any other way of splitting up this number. It's, can I get an 8, 27, 64, or 125? That's all you should focus on. So you have a target. Same thing with square roots. It's a longer list. So in my opinion, square roots are more difficult because there's more numbers to check. Right? We have a pretty long list here of numbers that we're supposed to know that we can take the square root of. And so you have a lot more to check. When it's a cube root, there's just 4 numbers. And so you just focus on trying to get one of those 4 numbers here. And then as soon as you can, then you can simplify it. All right, let's take a look at another example. So we have, again, it's a 4th root, which again, I know sounds terrifying, but this is also an easy one because there's not that many numbers that we can take the 4th root of. Don't worry about how many different ways you can split up 405. What we're looking for in specific with 4th roots is either a 16, an 81, or a 256. If it's not one of these numbers, it's not going to simplify. So I focus on the numbers that I have memorized that I know I can take the 4th root of. 16 doesn't work here, but 81 does. All right, so we'll try 81. It's going to be 81 times 5. That gives me 405. That way I'm not wasting my time looking at other options for 405 that would not do me any good. I only want these numbers when it's a 4th root. If it's not one of these numbers, it doesn't work. It doesn't simplify. So just focus on these. So 4th root of 81, 4th root of 5, right? So we apply the 4th root to each number separately. The 4th root of 81 is 3. The fourth root of 5 doesn't simplify, so we copy it down. All right, so we'll do the same thing here with 300. Now this one you got to be careful about because it's a square root. So you go back to your list of square root numbers and you might start with 4. 4 actually works, right? 4 times, what is it going to be? 75, I think. 4 times 75. And then you apply the square root to each of these separately. You get 2 here from that. Don't write that down though, because this is not the best way to deal with this problem. The issue is that 75, you can't just assume, okay, that doesn't simplify. You have to, like here, I'm not really making a big deal out of it, but fourth root of 5 is not going to simplify to anything else. But I don't just assume that, I think about it. Could this be simplified anymore? No, it can't be simplified anymore. But 75 can be simplified more, right? 75 could be split up again as 25 times, not 2, 25 times 3, right? And then we can apply the square root again and we get another 5 out of it. So the important thing about simplifying these radicals is that you get as much of the number outside the radical as you possibly can. So after you do one round of simplifying, you should check to see if it could be simplified further. And if so, then you just multiply those numbers outside the radical together. You'll get 10 here, right? What I want to do is kind of go back and start this problem over. And don't just take the first number you find here. You want to get the biggest number possible out of this that you can simplify. And so 4, it would be the smallest number that would work. 100 would work here as well, right? We can take the square root of 100, and 100 is a factor of 300. So we can split up the 300 x to the 4th power. We can split up the 300 as 100 times 3, right? And I can take the square root of 100. That becomes 10. That simplifies. And that's just taking care of it all at once instead of doing it one piece at a time. All right. It's not that it's wrong to do this way, just it's a little bit more work, and I'm fine with it if this is how you get the answer on the test. I'm not going to take points off because you took longer than you absolutely had to. I'm actually impressed when students do it this way and they are persistent and they keep breaking it down and simplifying it. That actually is a good sign to me, and I actually like when I see that students are doing that. But if you want to take care of it all at once, this is the way you'd want to do it. And then the x to the 4th power. So remember what we learned in 6.2 is that we can divide the power inside the radical divided by the root of the radical. And the root here is a 2, right? It's an invisible 2. It's a square root, which means this x to the 4th power is going to simplify really nicely with this square root because they divide evenly. 4 divided by 2 gives me 2. So I'm going to actually lump this x completely with the 100 since it's going to simplify nicely too. So all the stuff that simplifies well is going to go into this first group, and all the stuff that's left over that doesn't simplify is going to go into the second group. So that's the way I like to organize it. So now, again, we're taking the square root of this. So now I'll split up the square root, apply it to each one separately. The square root of 100 is going to give me 10. The square root of x to the 4th power is going to give me x squared, right? 4 divided by 2 is how I get the new exponent of 2. And then the square root of 3 doesn't simplify, so we just copy it down. And so that would be my final answer here. All right, let's take a look at another example. All right, so we want to simplify the expression cube root of 56x to the 8th power. Now I'm going to do things a little bit differently than you will see on Math Excel. I'm going to do it like I did the last problem, essentially. So what I like to do is split these expressions up into a good pile and a bad pile. In the good pile, you'll have all the things that simplify nicely where the radical is just going to go away. In the bad pile, you have all the junk that's left over that isn't going to simplify. And so you want to get as much stuff into the good pile as you possibly can. All right, so for cube root, remember the numbers we can take the cube root of are 8, 27, 64, and 125. Those are the ones you're supposed to memorize. These already are too big for 56, and 27 doesn't work. So really it's just 8 or nothing, right? Either we can get an 8 out of this or it's not going to simplify. And we can, right? For 56, that can be written as 8 times 7. We'll put 8 in the good pile because we can take the cube root of 8. It simplifies to 2. And then we put 7 in the bad pile because it won't simplify. We'll do the same thing with x to the 8th power. Now remember, this will simplify if the power can be divided by the root. Here, 8 does not divide by 3. So as a whole, this will not simplify nicely. So we're going to have to split up the x as well. We didn't have to do that in the last example because the whole thing simplified nice. But here, 8 powers of x is not going to simplify nice with x, or with a cube root, excuse me. So we'll have to split it up. Now what a lot of students will do is they'll say, thinking back to what we talked about in one of the earlier videos, cube root cancels out a power of 3, which is true, but you want to get the most powers of x out of this as you possibly can to simplify nicely. And so it isn't just that cube roots cancel out powers of 3, they will cancel out nicely with anything that's divisible by 3 as well. So you want the most powers of x that you could still divide evenly by 3. We have 8 to work with. That means we can actually take 6 powers of x and put it in the good pile, because 6 will divide nicely by 3, and so it'll simplify nicely. And that's the most we can get with the 8 that we have to work with. So we'll put 6 over here in the good pile. We'll have 2 left over that'll just have to go into the bad pile because it's not going to simplify. Right. Now we'll split up that cube root, apply it to each group separately. Right. And for the good pile, that group will simplify nicely. The cube root of 8 is going to give me 2. And then when I take the cube root of x to the 6th power, I'll divide. 6 divided by 3 gives me a new exponent of 2. Right. 6 divided by 3 gives me 2. And then the bad pile, if you did it correctly, you should double check. Is there anything here I could simplify more? But cube root of 7 doesn't simplify. Cube root of x squared, that doesn't divide nicely. There's no way to split it up to get more powers of x that will simplify nicely. So this isn't going to simplify, so we just copy it down. So what I wanted to say was, if you did it correctly, the bad pile just gets copied down every time. And this would be my final answer. And I got as much out of the radical as I possibly could. All right, so why don't you pause the video? We didn't really do much of that in the last couple of videos. I apologize for that, but why don't you pause the video and give this one a try, and then resume the video to see if you came up with the right answer. So we're going to split this up into good pile and bad pile. For a fourth root, the numbers we can take the fourth root of are 16 and what's the one after that? I'm drawing a blank all of a sudden. 81 and 256. Right? Those are the only 3 numbers I said you should memorize as numbers you can take the fourth root of. 81 clearly doesn't work. It's way too close to 96 to be a factor of it. 256 is too big. So again, it's 16 or bust here, right? So I'm going to give 16 a try. 16 divides into 96 and gives you 6. So it is a factor of 96. 16 times 6 is what equals 96. I'll put 16 in the good pile because that's the one that will simplify nice. 6 goes into the junk pile because it's not going to simplify at all. For x to the 4th power, that power of 4 can be divided by the root of 4. So all of the x is good because all 4 powers of x will simplify nicely with that 4th root. So I'm putting all 4 powers of x into the good pile. But that's not the case with y, right? 6 cannot be divided by 4. So those don't divide evenly. So I'm going to have to split it up, and I'll put as many powers of y into the good pile as I can. It just needs to be a power that can be divided by 4. And the only thing that can be divided by 4 that's less than 6 is going to be the number 4 itself, right? So I'll take 4 powers of y and put it in the good pile. That'll simplify nicely with the 4th root. And I'll have 2 powers of y left over that have to go in the bad pile. All right, so I apply that 4th root to each pile separately. When I apply the 4th root to the good pile, each of these individually should simplify nicely. The 4th root of 16 will be 2. The 4th root of x to the 4th power will just be x, because that 4th root cancels out that power of 4. Or if you want to divide, 4 divided by 4 is going to give me 1 here. X to the 1st power, which is just x. Same thing happens with y. And then the bad pile just gets copied down. We'll have the 4th root of 6y squared left over. All right, let's take a look at another example. I got a lot of examples in this section. This one is a little bit of a different type of problem, where we actually will use both directions of the rule that we're learning, the product rule. So individually, 21 and 6 do not simplify, right? The square root of 21, there's no way to split that up. You can write it as 3 times 7 if you want, but the square root of 3 doesn't simplify, the square root of 7 doesn't simplify. So nothing, you can't get anything out of 21, same thing with 6. So as separate numbers, these do not simplify with the square root. What we'll have to do here is multiply these square roots back together into a single square root, right? That's using the same rule, but in the other direction, right? So instead of splitting a single square root up into two, we're taking two square roots and combining them back together into one. Excuse me. All right, so now we can multiply these together. So 21 times 6 is going to be, I think it's 126. Let me think about that. So 6, yeah, 126. All right, so we have the square root of 126. Now that we put those numbers together, what we're going to try to do is simplify it by splitting them up in a different way. So instead of having 21 and 6, is there another way I could rewrite 126 so that something does simplify? Right? And so let's think about it. The numbers we can take the square root of are 4. I don't think 4 works there. 9. I do think 9 works, actually. So we'll put 9 here. 9 divides into 126. We'll get 1 and 14. We'll have 14 left over. Right? And that's good because 14, there's no way to split it up to get anything more out of it. That will simplify with the square root. So that means this is the optimal thing to do here. So we'll apply the square root to each number separately. The square root of 9 gives me 3. The square root of 14 just copies down. And that's going to be my final answer. Right? So this one, I'm going to do the same way. You could simplify these for, here's what I don't like about this problem. I could simplify this one actually, right? This will be 9 times 3, and that simplifies. And the square root of 60, we can rewrite 60 as 4 times 15, and that will simplify. And you'll get some results here, but then you have to multiply those results together, and then you'll have to simplify your result one more time. So if you count, if you're keeping count, you are simplifying 3 different times. You're simplifying this square root, and then the answer that you get will have to be simplified also. That's 3 different square roots we're simplifying, and I feel like that's a lot. So you could do it that way. Math Excel may, in fact, suggest you do it that way, but what I like to do is I just want to simplify once. So I'm going to multiply these together into a single radical, and then just simplify that single radical. Right? So think of this as 27 times 60. I don't know, now I'm really thinking maybe this is a bad idea because that's going to be a really big number. And I was thinking I had another clever way of doing it, but really the other way I was thinking of doing it really is kind of like what we were doing over here. So I don't know, maybe this is not a good idea. Let me get my phone real quick so I can see how big that number is. And then maybe I'm going to change my mind. So let's see. All right. So let's find out what that is. 27 times 60 is 1,620. That is pretty big. And yeah, we could split it up in some particular way, but it may not be the most optimal way, so we might have to split up again. We might end up having to simplify 2 or 3 times if we do it this way anyways. So I think I'm going to change my mind on this. I feel like this may not really work out all that well because of how big that number is. The idea I had in mind was to multiply them together in the same radical and then split them up like this. But that's really the same thing as what we're doing over here. So might as well just do it this way. So let's go back to this. Let's abandon that plan. Let's simplify the radicals individually first, right? So I'm going to split up, as I mentioned before, 27 as 9 times 3. We apply the square root to each of those separately. So here I'll get 3 square root of 3 when I simplify that. For 60, we're going to write that as 4 times 15 and apply the square root to each of those separately, and we'll get 2 square root of 15. Now you might say, well, why didn't you write 60 as 6 times 10? I'll get that question in class sometimes. Because if you wrote it as 6 times 10, you can't take the square root of 6 and you can't take the square root of 10. Nothing simplifies from that. So you're really no better off than you were before. Right? So you want to make sure you're splitting this number up in a way that something will simplify from it. Now what we have to do is multiply these together, and the way I like to describe it is you multiply together what goes together. So the numbers outside the radical, because it's all multiplication, so basically we're rearranging the order we're multiplying in, and we'll multiply the numbers outside the radicals together. So 3 times 2 is going to give me 6. Right? So multiplying those together, and then we'll multiply the radicals together because those go together. Right? Square root of 3 times the square root of 15, using that same rule we used over here, we can multiply those together and we'll get square root of 45. All right, so 3 times 15 gives me 5, and that multiplies together inside of a single radical. And then we can't just stop here and say, okay, that's my final answer. we have to see if this could be simplified even more. And it can be, right? So like I mentioned, we're simplifying 3 different times in this problem. The 45 can be rewritten as 9 times 5. We did this one at the beginning of the video, right? We apply the square root to each factor separately. The square root of 9 is going to give me 3. The square root of 5 just copies down. And then I'll copy down the 6, which is being multiplied to that. And so I'll have 6 times 3 times the square root of 5. And again, multiply together what goes together. 6 times 3 go together to give me 18. So I'll get 18 square root of 5, which would have been kind of hard to find from such a big number that we had over here. So I guess I will have to say, I think the best way to do this, even though it's kind of annoying having to simplify multiple times, simplify the radicals first, then multiply them together, and then simplify that answer one more time. All right, let's take a look at another example. So here, now this one, I'm going to advocate we do it the other way, the way I abandoned in the last example, because when you multiply these numbers together, they're not that bad, right? Now we could split up the B and the C and simplify first, but I think it's better in this case, instead of simplifying the radicals individually and then multiplying them together and simplifying a third time, this actually works out pretty nice just to multiply them together into a single radical and then just simplify that single radical all at once. So you're just simplifying once instead of 3 different times. So same spiel as the last problem, except this time it actually works out really well. So we'll multiply these square roots together into a single radical. So we'll have 5b to the 3rd power times 15c to the 4th power. So multiply these together. 5 times 15 gives me 75. And then we'll have b to the 3rd power, c to the 4th power. And just like we were doing a few pages ago, now we'll split this expression up into a good pile and a bad pile. The 75, we're going to want to split that up as 25 times 3, right? You want a number that you can take the square root of. For 75, we can get a 25 out of that. That will simplify nicely with the square root. There will be a 3 left over that doesn't simplify, that we just put into the bad pile. For b to the 3rd power, the 3 doesn't divide evenly by the 2, right? It's a square root. That means we want powers that can be divisible by 2, or that can be divided by 2, right? And 3 doesn't divide by 2. So that means we're going to have to split up b also. We'll take as many powers of b as we can to put in the good pile. As long as that exponent can be divided by 2, it's going to simplify nicely. So we have 3 powers to work with. I'm only going to be able to grab 2 of those powers, because 2 can be divided by 2. And that means I'll have 1 power of b left over that has to go in the bad pile. And then with c to the 4th power, that's actually all good, right? We don't need to split that up because that exponent of 4 is already divisible by 2. So that will simplify completely on its own, so we don't need to split it up. So put the whole thing in the good pile since the whole thing simplifies. And there's no c's left over to go in the bad pile. Right, so now we'll apply the square root to each group separately. The square root of 25 is 5. Excuse me, sorry about that. The square root of b squared is b, right? Because again, 2 divided by 2 is going to give me 1, b to the 1st power. And then c to the 4th power, the square root of that, again, we'll take 4 divided by 2, which is going to give me 2. And then the square root of 3b gets copied down because nothing in it simplifies, and that'll be our final answer. And that way, you see, we only simplified one time. We didn't simplify twice and then have to simplify our result after that. I'm going to advocate the same thing here. We'll multiply these together into a single cube root. We'll put the 16 first, and then we'll have y. These actually are, I didn't realize, they're both the same variable. So we'll multiply, let me undo all that. We'll go ahead and I want to write it out to make sure you're able to follow along with it. So we're going to multiply these together inside of a single radical. So we'll have y to the 10th power times 16y to the 11th power. So in this case, the number has nothing to multiply to, so we'll just write that down first. And then the variables, because the bases are the same here, you can multiply these together and we'll add the exponents, right? So we'll have 10 plus 11, which will give me 21. Right, now the 16, we need to split that up because you can't take the cube root of 16. We're going to have to split that up as 8 and 2 because we can take the cube root of 8 and we'll have a 2 left over that goes into the bad pile. And for the y, we actually don't need to split this one up because 21 is already divisible by 3. So again, it's all good. all of those powers of y will simplify nicely with the cube root, so we don't need to split it up. So we'll put all 21 powers into the good pile, since that's going to divide nicely. So we apply the cube root to each pile separately. The cube root of 8 will be 2. The cube root of y to the 21st power will be y to the 7th power. Because again, you'll divide. 21 divided by 3 gives me 7. And then this gets copied down. Cube root of 2 doesn't simplify, we just copy it down. All right, so that's how those problems work. Got a couple of more here that just kind of to push the limit here on these things. Again, with the variables, I think it's easier to multiply these together, but we're going to run into the problem of these numbers are going to be kind of big if we multiply them together. So we might keep the numbers separate, but multiply the variables together. Let's see if we can make that work. So we have 18 times 27. That's 486. It's kind of a big number to deal with in a square root. So here's what I'm going to do. We'll multiply these together. And again, there's more than one way to get through these problems, so you don't have to do it the way I'm suggesting. You could look at Math Excel to see how they suggest you do it. I'm going to write this as 18, a to the 9th power b, times 27, a to the 10th power b to the 8th power. Right, so we're going to multiply these together into a single square root. Then I'm going to reorganize this. I'm going to put the numbers together, but not multiplied together. I'm just going to write them side by side. 18 times 27. Let's keep them separate so that they're smaller and maybe a little bit easier to manage. But with the variables, I want to just multiply those together. A to the 9th power, a to the 10th power. You add the exponents. 9 plus 10 will be 19. And then b to the 1st power times b to the 8th power, that's going to give me b to the 9th power. All right. So now I'm going to start splitting things up, and I'm just going to split these numbers up separately. So instead of having them as one big number as 486, I'll just keep them separate and split them up individually. So 18, for a square root, I would split that up as 9 times 2. For 27, I would split that up as 9 times 3. And then before I accept this as my bad pile, I'm going to look to see, what does this give me? This gives me 2 times 3, which is 6. Could that be split up more so that more of it could go into the good pile? In this case, the answer is no, right? 2 times 3 is 6. There's no way to get any more numbers out of that to move over to the good pile. So all of this will just stay in the bad pile. And we're done with the numbers, right? We split up 18, we split up 27. We looked at the bad pile with those numbers together, and they all stay bad, right? Nothing from the number 6 can be moved over to the good pile. So we're good to go. We'll do the same thing with a to the 19th power. We'll split it up. We have to split it up because the root here is 2, and 19 cannot be divided by 2. So we're going to have to split a up as well. We'll put as many powers of a as we can into the good pile, and we want the highest power here possible that can still be divided by 2. So we have 19 powers of a to work with. We'll put 18 of them in the good pile, because 18 can be divided by 2, and that's the biggest number I can get that can still be divisible by 2. And I'll have 1 power of a left over that goes in the bad pile. We'll do the same thing with b. What's the highest power of b I can put in the good pile? It'll be 8. Right? We have 9 powers to work with. I'll put 8 of those powers in the good pile because 8 can be divided by 2, so it'll simplify nicely. We'll have 1 power of b left over that goes in the bad pile. All right. Now we apply the square root to each pile separately. The good pile should just completely simplify. So we'll have square root of 9, which is 3, times another square root of 9, which is another 3. The square root of the square root of a to the 18th power, we're going to divide that by 2. 18 divided by 2 means I'll have a to the 9th power. And then for b to the 8th power, we'll divide that by 2. We get b to the 4th power. And then the bad pile copies down. We'll get 2 times 3, which is 6, AB. And then, I don't know, we could have handled this in a little bit of a different way, but I don't know, I left it like that. But we want to multiply those 3's together for sure. So 3 times 3 is going to give me 9. A to the 9th power, b to the 4th power, times the square root of 6ab. And that's how that one simplifies. And I think this should be like the worst case scenario problem that you should have of this type on the homework. So if you can do this one, you should be able to handle any of the ones that you're given. either on the homework or on the test. All right, let's take a look at another example. Okay, so we encountered a couple of, well, maybe not even a couple, one of these examples in the previous video where we're trying to multiply two radicals together, but they are not the same root. So you'll notice, it's kind of a long ways back here. I don't know how quick I can get back to it, but this rule that we're using to simplify throughout this entire video only works if the roots are the same, right? You can multiply two radicals together into a single radical if those radicals have the same root. Let me put it that way. And so we have now reached a problem where that's not the case. So all of these problems that we just got done doing, right, they're all the same root, right? All the radicals have the same root. These are both square roots. These are both square roots. These are both square roots. These are both cube roots, right? These are both square roots. So they're all the same. This one, we have a cube root and we have a square root. They do not multiply directly together like that. So what we'll have to do to multiply these together is what we did in the last video. That's why I kind of did that example in 6.2, is we have to rewrite these as rational expressions. Not expressions, what am I saying? As rational exponents. So we're going to rewrite these in exponential form. That's what I wanted to say. And then as exponents, we'll find a way to make them go together as a single radical. Okay, so we're going to rewrite this radical as an exponent. The base will be 10. It's a cube root, which is a 1/3 power. Right? Really helpful to just know that. A cube root is a 1/3 power. Here we have this radical. We'll write this as an exponent. It'll be 7. It's a square root, which is a 1/2 power. We're going to multiply these two together. Now, we actually cannot even multiply these together as exponents because the bases aren't the same. But the trick we're going to use is what we did in section 6.2, which is we will find a common denominator. Even though we're not going to add these fractions together, let's get the denominators to be the same. And so the common denominator here would be a 6. So I'll multiply 2 to the top and bottom of this fraction. That's going to give me 10 to the 2/6 power. And I'll multiply a 3 to the top and bottom of this fraction. That's going to give me 7 to the 3/6 power. And then we can separate the numerator from the denominator. I'm going to rewrite 2/6 as 2 times 1/6. And I'm going to rewrite 3/6 as 3 times 1/6. And because we have the same exponent on both of these factors, that exponent can be taken outside parentheses. And so I'm going to have inside parentheses 10 to the 2nd power left over. That 2 will be left behind here, times 7 to the 3rd power. That's what's going to be left behind here. And then this power of 1/6 will be taken outside parentheses. So it'll be raised to the 1/6 power, which is something I can now write as a radical. So I can rewrite this power of 1/6 as a 6th root. And then inside the 6th root, we'll have 10 squared times 7 to the 3rd power. And this is going to be a really big number, right? 10 squared is 100 times 7 to the 3rd power. I don't know why I remember this one. I guess because it's similar to 3 to the 5th power. 3 to the 5th power is 243. 7 to the 3rd power, I just happen to remember, is 343. And then we can multiply those together. So we'll get the 6th root of 343 with a couple zeros after it. So 34,300. And that's what we get when we multiply those two radicals together. Looks like I might have cut off some of the directions because this doesn't make sense, right? Multiply and simplify numbers, that doesn't quite make sense. So I think there's more directions there, but I'm pretty sure this is what you were expected to do. All right, let's look at another example that's actually very similar to that one, except this time we have variables. And I think you'll find, I think it's easier with variables. I think numbers, I know a lot, the perception is math makes sense with numbers. It's more difficult with variables. But I think the opposite is true when it comes to radicals. I think the variables are easier to work with. They make more sense. They're easier to figure out. And it's the numbers that are hard to work with when it comes to radicals. So we're in the same dilemma here. We can't multiply these radicals together because they're not the same root. This is a square root. That's a 5th root. So we're going to do the same exact strategy. Rewrite this as an exponent. We're going to have this as xy to the 3rd power raised to the 1/2 power, right? A square root is a 1/2 power. Here we'll have x to the 7th power y raised to the 1/5 power, right? Because a fifth root is a 1/5 power. Now you could go ahead and distribute these fractions into the parentheses, these exponents here, but I think it might actually be easier if we just leave them outside the parentheses. Let's go ahead and get a common denominator. Even though we're not going to add these fractions together, let's get the denominators to be the same, and then we can bring that denominator outside parentheses. All right, so the common denominator here is going to be 10. So I will multiply a 5 to the top and bottom of this fraction. That's going to give me x y to the third power raised to the 5/10 power. And then here, I will multiply a 2 to the top and bottom. And that's going to make this x to the 7th y raised to the 2/10 power. And instead of going through the extra writing of splitting it up, I mean, we're going to split this up as 5 times 1/10. This will be 2 times 1/10. The ultimate effect is that we're taking this common denominator outside parentheses, and it'll stay in the denominator, right? So what's going to happen is we're going to get this big parentheses here, and outside of that parentheses we'll have this denominator of 10. And since it has to stay in the denominator, we'll have to put a 1 in the numerator. So we're bringing that denominator of 10 outside parentheses as 1/10. What's left inside the parentheses is we have this x y to the third power. It'll still be raised to the 5th power, right? There's a 5 that was left behind here. And then we're going to have this x to the 7th y that is still going to be raised to the 2nd power, right? There's a power of 2 left here. Now I'll go ahead and distribute. So instead of distributing the fraction and having all these fractions all over the place, I just decided to get rid of the fraction by bringing the common denominator outside parentheses. And now it's out of the way. Now I can go ahead and distribute this power of 5 into the parentheses here. I'll get x to the 5th power, y to the 15th power, because this is the case where you multiply the exponents. Do the same thing here. We'll get x to the 14th. I don't know why I'm writing 17 when I say that. X to the 14th power, y to the 2nd power. And that's still being raised to the 1/10 power. And we don't want to leave more than, how do I want to say this? I don't know, maybe it's not the right rule to apply here, but we can simplify this further. Let's just say that. So we'll multiply the x's together. This is the case where you add the exponents, right? So we'll have x to the 5th times x to the 14th. We add those together, we get x to the 19th. And then we'll multiply the y's together, and we add the exponents. We get y to the 17th power. And that's going to be raised to the 1/10 power. Now we can write this as a single radical, right? This 1/10 power means we have a 10th root of x to the 19th power, y to the 17th power. All right, and I just had a terrible thought about this, that we actually aren't done. I really didn't plan for having any more room here. So let me go ahead and move this to a new page so we can finish the problem. Because it does say multiply and simplify. Again, the rest of the directions are cut off, but once you multiply it into a single radical, they want us to simplify it. Right? And so let's go ahead and copy that over to a new page. So we need to simplify this expression. Put that over here. Whoops, that didn't work. Let's try it again. All right. So let me go ahead and complete this radical symbol there. So now we're going to split it up into good pile, bad pile. And it's a 10th root, which means I only want exponents in the good pile that can be divided by 10. So I have 19 here to work with. The most I can get out of that can still be divided by 10 is 10, right? We'll get x to the 10th power here. That'll simplify nicely with the 10th root. We'll have 9 powers of x left over that go in the bad pile. The same thing happens with y. We can get 10 powers of y into the good pile. We'll have 7 powers of y left over that go into the bad pile. We apply the 10th root to each group separately. The 10th root of x to the 10th power, again, the 10th root cancels out that power of 10, and I just get x. The 10th root cancels out the power of 10 on the y as well. So we'll just get x times y, and then the bad pile just gets copied down. We'll have the 10th root of x to the 9th power, y to the 7th power. And I believe this is what you're going to want as your final answer for this problem. Now I want to go back and check the previous example because I wasn't really thinking, could we possibly simplify it? So let me double check to make sure the number 1 couldn't be simplified. And if you go back to here, you might say, oh, you have to figure out this number. You don't have to actually analyze this number here. That's a really big number. You can just go back to here when you had it factored out. Sixth roots will only cancel out with powers of 6, or powers that can be divided by 6. And you don't have enough powers here for that to happen, right? The highest power you have here on the 10 is a 2, so that's not going to simplify nicely with the sixth root. And the power you have on the 7 is a 3. You need at least 6 powers of something here for this to simplify. And so this actually doesn't simplify that, so we can just leave it the way it is, thankfully. All right. There's one more topic in this video, so I'm sorry, this video is going a little bit longer than I would have expected. But this topic is kind of a quicker topic. It's the quotient rule, which is really the same idea as the product rule, except it's for division or for fractions. So if you're taking the nth root of a fraction, that root can be applied to the top and the bottom of the fraction individually. So that's going in this direction. That's how the rule can be applied. You can also use the rule in this direction, where if you're dividing two radicals that have the same root, you can divide them into a single radical. And sometimes that can be helpful. So let's look at a few examples and then we'll be done. I'll try to go as quick as I can here. So this one, you could try to simplify the cube root of 24 by splitting that up. But let's deal with the division here first. And if you do that, it actually simplifies really nicely. So we can divide these back together into a single radical, right? That's using the rule in this direction, going from right to left. We're taking two separate radicals that are being divided and writing them together into a single radical, right? And so I can write this as a single radical by putting the 24 on top and the 3 on the bottom and putting the single cube root on top of the whole thing. And by having them together inside the single radical, they can now reduce or cancel each other out. 24 divided by 3 is going to give me 8. And then I'll take the cube root of 8, which just gives me 2. Right. So while they're in separate radicals, they technically cannot be canceled out. But once you get them together inside the same radical, they can be reduced. And then once you reduce it, usually it simplifies pretty nicely from there. Same thing's going to happen on this one, right? We can rewrite these into a single square root. We'll have 90 over 10 inside of that single square root. And then now that they're inside the same radical, they can be reduced. So 90 divided by 10 gives me 9. The square root of 9 is going to give me 3. So that's how that one will simplify. There's a little bit of an unspoken rule. It's not unspoken. We haven't spoken it yet, though, of you cannot leave radicals in the denominator. We're going to learn more about that later, I think in 6.5. But it's a rule that they are still following in this section. So these problems should all simplify where there's no radicals left in the denominator. So, which means they kind of give you nice problems that usually work out pretty nice because they're trying to honor that rule, even though we haven't talked about it yet. All right, so again, the directions got cut off here, but we want to divide these. So let's do the same thing we did on the last problem. We'll write these inside of a single square root. We'll have 4xy to the third power on top. We'll have 2x on the bottom. Now that these are inside of a single square root, we can start canceling things out. The x's cancel out. The 2 cancels out with the 4. It leaves me with a 2 on top. And so the denominator completely goes away, which like I said, they kind of have to do that because they're not allowed to leave radicals in the denominator for these problems. What we're left with is 2y to the third power. Now you might be tempted to just leave your answer as that, but y to the third power can be simplified with the square root, right? The square root, again, the invisible number here is 2, and there's enough powers here to interact with that. And so we need to try to simplify it. Now 3 doesn't divide by 2, but we can split it up and get a power here that can divide by 2, so it will simplify somewhat. And so the 2 cannot be split up, right? The 2, there's no way to split that up. It doesn't simplify with the square root, so 2 goes into the bad pile. And then y to the third power, we'll split that up. We'll put 2 powers of y in the good pile, because that'll simplify nice with the square root. We'll have 1 power of y left over that goes in the bad pile. You apply the square root to each of those separately. The square root of y squared is y. You don't have to use absolute value for these problems. That was only something we did in 6.1. And then this bad pile, the square root of 2y, just gets copied down. And so that's how that one simplifies. All right, so why don't you pause the video? I know this one looks really scary. It's a fourth root. There's a lot of crazy stuff going on here, but it's really the same principle as this. So pause the video, give this problem a try, and then resume the video to see if you come up with the same result. All right, so what you want to do with this one is like the last example. You want to rewrite this as a single radical, so it'll be a single fourth root. of 162 x to the 17 y to the 25th. I know it's a lot to think about, but we're going to divide that by 2x y to the 17th. So a lot of stuff is going to cancel out here, which will be nice. We can divide the 2 into the 162, and that'll leave me with 81. We can get rid of 1 power of x, and so 1x cancels out here. We'll have 16 left over here, and 17 powers of y. So getting rid of 17 from the 25, I will have 8 left over, right? And so we're going to get the fourth root of 81 x to the 16th, y to the 8th. And this is great because everything here simplifies. It's all good pile stuff. We don't need to split this up. Nothing goes into the bad pile because all of these will simplify nicely with that fourth root. So the fourth root of 81 is going to be 3. Now be careful about this. I get students that will make a mistake with this on the test. They'll think, oh, the fourth root of 16 is 2, and they'll write the answer as 2 here for the exponent of x. But that is not correct, because you're not taking the fourth root of 16, you're taking the fourth root of x to the 16th power. And to do that, you are dividing here. 16 divided by 4 gives me 4. So that's the exponent we should have there. Same thing with this, right? We're not taking the fourth root of 8, it's the fourth root of y to the 8th power. And to do that, we will divide. 8 divided by 4 is going to give me 2. And so that's how that one simplifies. All right. Now these are the same kind of problems, but in the reverse direction where they're already together inside the same radical, but they don't really simplify that way. Nothing can be canceled out or reduced or anything like that. And so what we want to do is split them back apart so that maybe we can simplify these square roots. So I'm going to apply the square root to the top and bottom of this fraction. So I'll have the square root of 144 on top, the square root of y squared on the bottom. The square root of 144 is 12. And here that square root cancels out that power of 2, and we just get y. And like I said, technically that probably should be the absolute value of y, but in this section they don't want us using absolute value when we simplify these things. We'll do the same thing on top, or not on top, same thing with this example over here. We'll apply the square root to the top and the bottom of this fraction. And so we'll have the square root of 9y to the 5th power on top, and on the bottom we'll have the square root of x to the 8th power. So here's where I said they are sort of beholden to this rule that you don't maybe know about yet, but the denominator will always simplify nicely. So the square root of x to the 8th power, again, we're dividing. 8 divided by 2 gives me x to the 4th power. Here, this one doesn't have to simplify nicely. The top doesn't. The denominator always does, but the numerator might not. And in this case, it doesn't. We're going to have to split this up because the 5 doesn't divide by the 2. So that's not going to simplify completely. So we're going to have to split this up. The 9, however, doesn't need to be split up because the square root of 9 does simplify nicely. So we'll just put 9 in the good pile. We'll take as many powers of y as we possibly can, take the square root of, which means we want the highest power that can be divided by 2. We have 5 to work with here, so we want to put 4 powers of y in the good pile. We'll have 1 power of y left over that goes in the bad pile. We apply the square root to each of those separately. The square root of 9 gives me 3. The square root of y to the 4th, again, we divide. 4 divided by 2 is going to give me y squared. And then the bad pile we just copy over. So square root of y just gets copied over here. And that's how that one simplifies. All right. Let's simplify the 5th root of 32x to the 8th power over y to the 15th power. Same thing that we did on the last couple of examples. We will apply the 5th root to the top and bottom of this fraction. So we will have the 5th root of 32x to the 8th power on top. And on the bottom, we'll have the 5th root of y to the 15th power. Kind of the same thing that happened in the last example. The denominator, it has to simplify nicely, and it does, right? We'll divide. 15 divided by 5 gives me y to the 3rd power on the bottom. On the top, the 5th root of 32 actually works out, right? You don't have to split up the 32. It's ready to be simplified as is. So we will put that all into the good pile. But the variable is not ready to be simplified as is because it doesn't divide evenly, right? 8 cannot be divided by 5 evenly. So we're going to have to split that up. We'll put 5 powers of x in the good pile. We'll have 3 powers of x left over that go in the bad pile. We apply the 5th root to each pile separately. The 5th root of 32, it's one you want to have memorized. It's equal to 2. The fifth root of x to the fifth power, that fifth root cancels out that power 5, and so we just get x. And then we'll have the bad pile just copied down here. It's the fifth root of x to the third power. All right, so this is actually the last example in the video. So why don't you pause the video, give this problem a try, and then resume the video to see if you came up with the right answer. First, you'll start by applying that cube root to the top and the bottom of the fraction. And then you'll simplify, and I always just start with the denominator because that one always simplifies nicely. That cube root cancels out that power of 3, and so we'll just have y in the denominator. On top, we're going to have to split this up. The 27, however, does not need to be split up because we actually can take the cube root of 27. So we'll put that entire number in the good pile, but the x has to be split up. We'll take 3 powers of x in the good pile. We'll have 2 powers of x left over that go in the bad pile. You apply the cube root to each pile separately. The cube root of 27 is 3. The cube root of x to the third power, the cube root cancels out the power of 3, and we'll just have x. And then the bad pile gets copied down. We have cube root of x squared left over from that. And that is how that one will simplify. So that concludes the video on section 6.3 on simplifying radicals.